Good morning, everyone. Welcome to our first session of the computing track of SBGames 2021. We will have my name is Luis Chamovic. I'm from Universidade Federal de Minas Gerais, and I will be chairing this first session. We have 4 papers, and each author will have about 10 minutes for presentation, and we will have 4 minutes for questions. You can pose your questions both on the Discord channel and on YouTube. Okay, so let's go to our first paper. The name of the paper, the title of the paper is Procedural Enemy Generation through Parallel Evolutionary Algorithms, and you will be presented by Leonardo Pereira from ICMC USP.
Hello, everyone. Can you hear me okay? I think everything's okay.
Yeah.
So, I'm Leonardo Pereira, and I'm going to present to you our project together with Breno, Viana, and Professor Claudio Toledo, which is the procedural enemy generation through parallel evolutionary algorithm. So, enemies are one of the core components of most video games, and there are plenty of research about intelligent agents to control the enemies, but not much on creating enemies with a diversity of status, mechanics, visuals, and other components. So with that in mind, we came with a research question that was, can we procedurally generate interesting enemies meeting a desired difficulty and with some diversity? So we studied evolutionary algorithms and we saw that they have been used with good results in the PCG literature. So they are able to evolve a whole population of solutions, which may bring some diversity with local optima. And we thought that they were good to adapt even when evolving complex enemies. So we thought that evolutionary algorithms may be able to generate our enemies. That was our main hypothesis. And to this enemy generation, we were able to do so. So those enemies you are seeing, those gray robots here, are enemies procedurally generated by our algorithm here in a game prototype that we developed and tested them. And how did we do this? So the representation of the enemies were just a list of parameters, and that we thought to be as general as possible, but according to our game prototype. So enemies usually have some health parameters, some damage, some attack speed, movement speed, an active time, a time they rest between attacks or any activity, and a speed for projectile for those that have projectiles, and some movement type or movement pattern, and a weapon type, for example, a sword, a bomb, a shield, or something like this. So the integer and float values have a range that we made some previous design tests and saw the minimum and maximum range that they still were good in the gameplay. And the types of movement and weapon were parameters that we developed and we could add to a list as much as we wanted, as much as your game needed. So we use these parameters to calculate the fitness. That represents the estimated difficulty of an enemy. So this fitness is basically the weighted sum of some parameters, of all the parameters. So the weapon, it has the damage from the enemy multiplied by a weight that each weapon type has. For example, a sword is stronger than nothing, and a machine gun is stronger than a sword, for example, and has a greater weight. For the projectile, the same thing. So for each projectile, maybe the enemy has a gun that has explosive rounds instead of normal rounds. So it has a weight attached to it and multiplied by the attack speed and the speed of the projectile. And for the movement component, we have a weight for the movement. So for example, aggressive enemies that follow the player have a higher weight than enemies that move at random. And then we sum everything here to the health, the active time, and 1 divided by rest time. So the most time the enemy is active, the harder it is. And this is our fitness. We want the algorithm to converge to a set fitness that represents the difficulty that the designer wants the enemy to have. So for the evolutionary algorithm, we created an initial population with random individuals. We use a crossover rate of 99%. And this crossover is the average for the numerical values, and for the nominal values, it's an equal probability to choose from the movement type from parts 1 or 2, for example. The mutation rate is 10%, and it is applied to each gene. Each gene has a chance to mutate, and the new value, when it mutates, is selected at random for said gene. So a value from the range or a nominal value from the possible behaviors. And we did some tests varying the population size and the generation stop criteria. The selection was a two individual tournament, so nothing much new in this. And we came up that the best parameters that we found was 10,000 individuals in the population and 30 generations for convergence. And for the easy fitness, we used 14 of fitness. The medium one 17.5 and the hard one 22.5. We did some previous tests and came to this result as some good easy, medium, hard enemy estimates. And it converging almost half a second for every one of these parameters. And on average, the whole population of the solution came more or less close to what we wanted. But we didn't need the 10,000 individuals. So what we did was to get some variety in the game prototype and the resulting population, we chose the 20 best individuals from set executions. So for each of these input parameters, we executed 200 times the algorithm to get this value. This is the average from 200 executions. But for each execution, we picked the 20 best individuals from our population to be placed in the game prototype, to be tested, and to use in any game that uses this algorithm. And from these 20 best individuals, the average of their fitness was basically exactly what we wanted. It converged pretty well with a very low standard deviation from these 20 best individuals. So this is what the best is. And how did we accomplish to converge it in only half a second? So we wanted our algorithm to be able to create content for possible future real-time applications. So we tried to optimize the performance through parallelism. As we were developing our game prototype in Unity, we used Unity's data-oriented technology stack, which is called DOTS, and it uses some entity component system that's a data-oriented design to better place data to be used in a parallel algorithm. It has a burst compiler and C# compiler optimized for parallel jobs, and the parallel jobs themselves. So each method for our evolutionary algorithm, the crossover, the mutation, the selection, is executed through a parallel job. So every one of the individuals, every one of the crossover is applied at the same time, obviously respecting semaphores. And with this, we can handle very large populations. So we can have a population of 10,000 individuals to converge in only 20, 30 generations, few generations, and this was done by the data-oriented design and the parallel jobs. So on the left, we have easy enemies on our algorithm. You can see that they shot slower, they move slower, they try to flee from the player. And on the right, there are the hard enemies. They are much faster, aggressive, they need more hits to kill them, they have larger health. So we can see that, at least visually, it looks like the algorithm can create diverse enemies on difficulty, right? The easy difficulty creates easy enemies and the hard difficulty hard enemies. So we also wanted to check if there was diversity from the 20, 10 best individuals in the population. We showed the 10 best because the graph would be very polluted if we use the 20 best enemies here. But this is the normalized values from 0 to 1 to all the parameters that composes an enemy. And this is the 10 best individuals used in one of our parameters inputs. And we can see that there is some variation between each of them. So even not focusing on it, we got some variety in our solution as we expected. So we conducted an experiment where we placed the game online and people could play it anonymously, and we collected some gameplay data and they answered some forms, Google Forms for us. And 16 players in total played the game. They could play as much as they wanted. They would select if they wanted the easy, medium, or hard difficulty and play as much they wanted in each of them, switch difficulties, anything they wanted, anytime they wanted. So most of the people played on the medium difficulty. And what we saw was that the easy difficulty was almost half, 50% of a win rate, which most known for medium difficulty. So we saw that our difficulty was not very good balanced. And the medium one, we had like 25% of a win ratio, and the hard one, only one attempt was able to win. So we saw that, okay, the difficulty was scaling as we wanted, but we made the game more difficult than we wanted. Even so, when asked at the end of the test if the combats against the enemy difficulty was adequate to the level they selected, For those that selected the easy difficulty, they strongly agreed, most of the players. For the ones that selected the medium difficulty, most of them agreed. There was some that disagreed, but most of them agreed. And for the hard difficulty also, most of them agreed that it was hard indeed. So this was good results. So it matched what the player was expecting, even if it was a little harder than what we wanted. And in conclusion, the evolutionary algorithm was able to converge accurately for 3 different difficulty settings, easy, medium, hard. The different enemies generated in the single run did exist, so even though it did not guarantee it by now, and it converged in a little above half a second, which is good for future real-time applications. And the difference in difficulty was perceived by the player. The created content was fun to play against. We asked the players also, and they said it was fun. It was very nice. This. And the major problem was that the difficulty experience was overall harder than expected. But we want to better balance this in future work. We want to use quality diversity solutions to guarantee this diversity. We want to test with more players. 16 is not that much. We want to do this in a real-time generation. So, for example, to create more content as the player continues playing. And we want our input parameters to be defined by some machine learning algorithm to adapt to players, and so we don't have to balance everything by hand. And that was it. Thank you very much. And if you have any questions, I'm glad to answer.
Okay. Thank you, Leonardo, for a very nice presentation. Now we have some time for questions. You can post your questions on YouTube or on Discord if you want. Let me check both. Nothing on Discord, on YouTube. As well, people are shy this time of the morning. I have a question. Your solution depends a lot on the fitness function, correct? Because if you have a low score, a low value on the fitness function, the enemy will be easier, and if you have a higher score, the enemy will be more difficult. But how do you set the fitness function? You show the equation, but this is by hand. How do you put together all that features?
Yeah. So what we wanted was to create a tool for designers to use, right? To create faster enemies and adapt to players. So, and we wanted something that could be more or less generalized to other games. So what we have right now is somewhat of a framework in the Unity environment. So we have some each enemy, for example, and each weapon, each behavior has a weight that we set it by hand, and we plan the designer to set it according to what best fits their game. So what they plan on the difficulty of a behavior and stuff, and so this is a little done by hand. And for the fitness value itself, so 15 is good enough or 20 is good enough. We had to do some tests, and that's why we wanted to create some machine learning algorithm to try to set these values through some gameplay data later. This was a little of a preliminary work on this, but we wanted to test if the idea was possible, if it could converge, and if we could do this. So our plan is to try to develop some kind of tool, some kind of framework that designers can use to create enemies for their games without much of the problem, aside from creating, of course, the scripts for our movement, the script for the weapons, and how the enemy acts overall.
Okay, there is a related question, but I think you already answered, about how do you define the weights, considering that this may affect the results. Have you noticed such thing?
Yeah. It's basically what I answered, and it does affect the results. So it's not a plug and play application, right? You must test a little and do some preliminary works, like on developing a game. So you need to do some tests inside before releasing to the public, and we want to make it faster to test this and create interesting enemies.
There was a time for one more question, a question by Flávio Coutinho. How does the proposed evolutionary algorithm compare to simply sampling from the parameters in a fixed range? Instead of applying the evolutionary algorithm, you just pick the values from a fixed range.
Yeah, so we didn't not have tests, so I'm only speculating here. But what we wanted through an evolutionary algorithm was to try to get this diversity for evolving a whole population, and so we don't have to apply the rules for all time. And it's a guided search better than a random sampling and try to guess some parameters and evolve different stuff by selecting at random and discarding the solution until we find something good. So we wanted to be able to evolve complex enemies. So, for example, we use a very simple approach in our game prototype, but if you think in a larger game, the enemies have much more components and then much more behaviors, and we can divide the whole behavior in different components, and each of them can have some weight. So we wanted to create something that could scale, right? So we wanted a solution that could be scaled to larger settings without we having to try to create random parameters for I don't know like 100 components of the system, and then okay, it matched what we wanted. No, try again. It matched what we wanted. No, try again. So the heuristic from the evolutionary algorithm it helps a little to converge faster and in a diverse way because of the population. So basically,
Okay.
this.
Great. Okay, so thanks again, Leonardo, for a nice presentation.
Thank you very much.
And let's move on to the next paper. Our next paper will be procedural generation of isometric racetracks using chain code for racing games. It will be presented by Erik, Jhones, Freitas do Nascimento from Instituto Federal do Ceará.
Okay, just to share my presentation here.
Okay.
Now you can see? Can you see?
Yes, we can.
Right. So my name is Erik Jhones, and I'm from the Federal Institute of Ceará from Brazil, and I will present our paper, Procedural Generation of Isometric Racetracks using chain code for racing games. And we are all from the Federal Institute, and this work is also one of the fruits of studies in the graduate program in computer science, PGCC. So I'm gonna just briefly present the background. So let's start by defining some essential concepts to understand our paper. Now, okay, let's start by talking about some challenges faced when developing racing games. When you want to produce some racing games, usually people face one or more of these 4 challenges. The first of them is related to the formula of development. Companies developed to racing game development already have their basic formulas, and they don't release them to the public. So every project outside these companies turns out to be super complicated at first. Another challenge is the high cost of production. Even more, the racetrack stage involves a specific effort by the development team to elaborate the new layout, change the geometry of the track, modify the terrain, and adapt the adornments to the perimeters of the runway. Another challenge encountered is that there are many different styles of racing games, and for each of them, the creation formula is entirely different. Current solutions for games production in general are not suitable for the production of racing games. And with tools right for other games genres, gaming engines are adapted with difficulty in the production of racing games, requiring adaptations in use. And another point that should be highlighted is what makes a racing game fun. It's evident that when making a game, regardless of genre, the creator expects the users to be able to enjoy as much of the experience as possible. For racing games, there are well-established studies that provide us with a formula of what a racing game must have to attract the attention of the general public. So, Togelius et al. Listed 5 main features that a racing game must have to be considered fun. The first of the states that the user expects to feel the vehicle's speed during the game. The second states that there must be a challenge to be overcome. Easy racing tracks are not exciting. The third talks about the difficulty in playing on the racing tracks being increased at the current speed. The fourth states that is interesting to vary the difficulties and the challenges. In other words, different race tracks with new challenges. And the fifth says that providing a feeling of drift and sleeping is very stimulating too. So, and that the PCG is the name, as the name says, is a set of techniques that help to create any kind of content automatically. In games, this can be used to create characters, generate scenarios, race tracks, and in general, 5 major aspects of PCG techniques can be listed: are the pseudo-random number generations, generate grammars, image filtering, spatial algorithms, modeling and simulation of complex systems, and artificial intelligence. And to finish the background section, we have the chain code. This is a very simple algorithm and very practical in applications involving computer vision. It was created by Herbert Freeman, and its operation is very simple and intuitive. Given a figure, the objective of the algorithm is to go through the entire edge of the figure and list in vector the index of the direction it is going to each step. As can be seen in this letter A, the chain code provided this list of directions, which, when transversed, it produces the shape of the letter A. And the most interesting thing is that from a list of directions, we can recreate any picture those, that the list encodes, just to follow the chain code in a best way. So all this brings us to this question: can you generate race tracks automatically in a simple way using chain code? Well, as we look at through the literature for papers on this topic, we were pleased to know that something like this has never been explored before. So we focus on developing this work, where our main objective is that it be something straightforward to be applied and reproduced. This work intends create a Racetracks database using the chain code algorithm to create a Racetrack, create a PCG for isometric to the racing tracks, and provide a karting game with the method implemented. Okay, this is our approach. I am going to explain detail what each of these steps in the flowchart does. So initially, we create a database with several images of racetrack circuits, but specifically card. And then the chain code was executed in each one of the images so that a new database with the list of directions was created. With the database, we can do anything. Here, we selected 10% of the database to build our new directions list. The choice is made randomly. With the list chosen, the new list is constructed using the element by element mode operation on the selected lists. And this selected list will be used to reconstruct the racetracks in the tool. However, it can be affected by the staircase effect, resulting from the element selection operation using the mode. To remove this effect, we use the algorithm developed by Douglas Picker. This algorithm is widely used to smooth curves. Finally, the resulting list is submitted to the Unity tool or any other, so that the Racetracks is automatically generated. The processor inserts the elements of the scenario, such as asphalt, barriers, trees, is the responsibility of the game developer. In our approach, we opt for a minimalist insertion of elements, since our focus is to develop the racing circuit generation method, not a game. After implementing our PCG method in our kart game, based on the Mario Kart games, we got some interesting results. First, visually, the generated tracks are actually playable and have different formats from each other. Furthermore, the generation time is incredibly low, on the order of a few seconds. Here, we can see the results of a questionnaire applied to a group in Discord. We made this card game that we created available to the folks, and we asked that after playing in a few times, they would fill in the questionnaire. The questions were about effects that make a racing game fun, and the goal was to assess whether our PCG method of racing tracks was really interesting. As you can see here, there is a consensus that the method was well received by the research audience. Only factor 5 had a negative impact, but this is due more to the game developed than to the method itself. And to conclude this, it is possible to create a 2D Racetracks with Gen code. This approach is efficient and simple and scalable. Our approach meets the criteria of what makes a racing game fun. Of the 5 factors mentioned by Tagalez et al., only one of them did not please the public. And the database created is free for public access. Another larger and more diversified database is under construction. So thanks for watching, and any questions?
Okay, thank you,
Okay,
Erik, for your presentation. Let's check if there are some questions on YouTube or on Discord. So far, no questions. I have a couple of questions. First of all, the fine-tuning, are you hearing? Okay. The fine-tuning part of the algorithm is do you need to use some manual fine-tuning, or it's just you just apply some other algorithms for doing the fine-tuning?
Okay, first, thank you so much for your question, right? So about this artist, right?
Mm-hmm.
Okay.
Oh. I think there was some problem with his connection. Let's see if he will come back. Just a quick note. We have only 4 minutes for questions, but you can continue to place your questions on YouTube. The authors will be able to answer on the chat of YouTube, like Leonardo just did for a question from Igor. Okay, let's see if Erik can come back. Let's wait just 1 minute to see if he will be able to come back to the presentation. Otherwise, we move on for the next paper. Okay. Okay, I think we can. He probably had some connection problems. Let's move on to the next paper, and then the questions can be placed on YouTube, or you can directly contact him on the Discord channel. Okay. Okay, so our next paper will be generative design applied to cloud modeling. It will be presented by Carlos Muniz. So we have 10 minutes, Carlos. Thank you.
Hello.
Okay.
Can you hear me?
Yes. You can just share your screen.
Just just hang on here. So I'm Carlos Eduardo Muniz, and I'm here to present generative design applied to cloud modeling. We have a cloud modeling tool that generates these Clouds on the left.
Just 1 second. We cannot see your screen. Did you share it?
Are you able to see the screen? Sorry?
No, no. We can't see your screen. Let's see if you can share it.
Let me check here. Sorry. I'm not being able to. Hang on. Someone.
Let's go offline for a second. Manuela,
Okay. Just go. Sorry.
Okay.
Sorry. Can you see now? Okay.
Not yet. Now we can see. Now we'll be able to see. Almost.
So is it working?
Not yet, but we cannot see it. No, it's not. You can move to the next slide. Let's see if it will change here.
I don't know.
No, we cannot see it yet.
Hang on. I have a bunch of windows here.
Let's go offline for a second. And Manuel, you can place the title of the slide, and let's try to solve this offline. Oops.
No. Sorry, guys. Is it working? Or just...
Not yet. Let's see now. It's not showing your PPT for some reason. Any case, we have your backup video.
Let me try again. Let me try again. I want to try to share again.
On YouTube, it seems that it's working. So try again. Maybe it's not. Try again to show.
Okay. I think I've got this time. Is it working?
Let's see. Let's do the following. Let's play your video, okay, and then you answer the questions based on the video. Can we do that?
Okay.
So Manuela, please, can you show the video, and then after the video, Carlos will be able to answer the questions.
My name is Carlos Eduardo Muniz. I'm from Federal Fluminense University, and I'm here to talk about generative design applied to cloud modeling, a work I've done with my colleague Wagner. So our idea is to generate clouds like this one, but that looks as close as this one. So we have a cloud generator that generates this kind of clouds using this kind of parameters. As you can see, we have a lot of parameters, like 152, and it's hard to know which are the best parameters to generate good-looking clouds. So we use an evolutionary approach to try to obtain these parameters. And we hope to produce a massive amount of clouds that may look as realistic as possible. And since we only need these parameters to store these clouds instead of the 3D model, we can have games with millions of clouds because each cloud uses 1 kilobyte or less. So here's what we're going to talk first with related works, then problem definition, then proposed method, results, and finally the conclusion and future works. Let's start with the related works. Cloud modeling was originally created with imposters, so it's 2D pictures using some lighting tricks to look like 3D or something like that. And one of the works that use this approach is from Harris, that does in real time. And then Abreu started with the procedural approach, using implicit functions to define the shape and modify it by noise. Spock implemented his idea in GPU. Peoples and Git used different ways to blend implicit functions, different noise functions, and there are other approaches like the one from M that use metaballs of procedural noise. So our work is actually a continuation of Montenegro et al., which is also a procedural modeling with some physics-based modeling. And we have our clouds defined as a volume, and each voxel of the volume is an implicit function that has a density, and we have these algorithms to find the density. And this volume has up to 10 primitives that may influence each of these voxels, as well as their area of influence. So these algorithms work in some similar way, but however, this second one allows to customize each primitive with more parameters than the algorithm one that use more global values for things that are defined by primitive in algorithm 2. We won't explain too much here. We want to continue Montenegro's work to find out the best parameters to create realistic clouds, because the work from Montenegro, we had to track these parameters on our own, and it is quite hard and quite not intuitive. So we have to find a way to effectively search the cloud shape space to find good-looking clouds, how to create these good-looking clouds, and we want a high level of variability of good-looking clouds as well. So that's what you're going to do with an evolutionary procedure. And this is our evolutionary procedure here. We start with a population. This population stays the same. However, we will use the clouds generator to transform it to image. And with the image, we use a CNN to rank these images, find out which ones look more like a cloud. So the best ones, the top half survives, are not changed, while the weaker half suffers mutation or crossovers depending on what we select. So our cloud generator uses a bunch of parameters, 152, to generate the cloud. And these parameters have up to 10 primitives and some global parameters as well. Here we have a fixed number of epochs, which will run the amount of times this loop will run. We have a fixed population, as I explained before. Half survives and the other half mutates or suffer crossovers. We store these parameters in one-dimensional arrays to facilitate the mutations, as well as data transfer between GPU and CPU. So we have some evolutionary parameters that we can set to determine in a mutation how many parameters can be modified and the intensity of these modifications. We also have ways to set a maximum and minimum value that each parameter can receive in a determined context to prevent awful clouds from being created. So because the space of parameters is unlimited, so we have to promote some limits, otherwise we're gonna generate some really awkward things. And the CNN has been trained with over 2,500 images, and they are all randomized. The synthetic ones have all the same size, which are not 90% of the population of the data set, while the 10% of the data set are photos from real clouds that we added to remove every kind of detail that the cloud generator does not generate. So we have to remove birds, smokes, mountains, trees, sun, moon, any kind of lighting that is not compatible with the cloud generator, among any kind of cloud that's not compatible with the cloud generator, among other things. So we use the real photos to train what are real clouds. Not only, however, what are not clouds, we use the synthetic image with what we don't want to be considered a cloud. That's why we focus much more on these synthetic pictures for no clouds. And we have two, the validation groups for no clouds also use synthetic clouds. But however, to define what is cloud, we have two validation groups. One with real clouds, which we use to validate what we trained, and the other with synthetic clouds to understand the behavior of the cement to clouds that we think that could be clouds. However, note that cement has different criteria for it, so it might not match ours. So these are some of the pictures we use to train what could be clouds. So these are real pictures from clouds in different resolutions, different size, different lighting situations, and among other things. And this is the architecture we used to detect small details and bigger details, and try to filter what could not be cloud. That's what we try to balance between filtering what's not cloud and allowing clouds. If we use very small architectures, we would filter too much, and that would not be good. We would have a hard time to generate good clouds. So this was found out experimentally. And the result, I have this confusion matrix for the clouds that were real, and the results were what we expected. While the confusion matrix for synthetic clouds, where the non-clouds were not considered clouds, which is exactly what was our objective here, to prevent any non-cloud from being considered cloud. While we have a couple of clouds that were considered non-clouds, which is expectable since the cement has different criteria of clouds than we have, and we don't have much control over it. So these are some results of non-clouds. They might have some artifacts that might be detected as non-clouds. And here's some of the clouds. This last one was detected as a cloud, but not of a high score. And these are some kind of clouds that we obtained after 15 epochs. So with using conservative parameters for evolutionary parameters, so with lower intensity of mutations and parameters that could be mutated. Here we use a higher intensity, but not much higher. And that's it. Our work proposed an evolutionary method to explore the space of parameters for generative design. And we use a CNN to calculate the fitness. When we rely, it's a brute force that relies on the filters, especially at rejecting bad-looking clouds to prevent regressions during the evolutionary process. So that's it. Our future works wants to use this framework to model other kind of assets such as rock, vegetation, buildings, and other kind of clouds. And we can also better calibrate our existing solution to use more aggressive evolutionary parameters to generate more variations. And that's all. Thank you for your attention.
Okay, Carlos, thank you for your presentation. Let's check if there are any questions on YouTube or on Discord. Not so far. I have a question when you mention that you want good-looking clouds or optimum shape alternatives on your presentation, in fact, you are using a classifier, right? That just says says if it's a cloud or not a cloud. There are no optimum metrics, right?
Yeah, exactly.
It's just a classifier trained with other images from clouds, synthetic or real images, and then you test if the clouds generated by your algorithm pass on this classifier, right?
Mm-hmm. Yeah.
Okay. And did you perform any kind of qualitative evaluation with users to check if the clouds looking good if the clouds look good in the opinion of users or not? It's just tested with the neural network.
We just tested experimentally, but we did not consult users. We don't have enough time to do that. Unfortunately, that deadline was quite tight. So it's future work to do that.
Okay, let's check if there are other questions. I have a final question. When you showed the results, there are some results that the clouds seem very similar visually, but one was classified as a cloud and the other one was not classified as a cloud. Why do you have this kind of difference? Were you able to detect why this happened?
It's a little bit hard to understand exactly all the criteria that the CNN understand what a cloud and what's not a cloud. We do not know exactly, but it's probably some minor details that may some sort of artifacts that it doesn't accept as a cloud.
Okay, we have a time for one more question. There are a question by Flavio on YouTube. The cloud generation seems to generate 3D clouds, but we saw only 2D images. Would it be possible to generate 3D volumes, or at least 2D slices of such volumes?
No, the generator actually generates 3D volumes, but we only found that our classifier is limited to image. So right now, that's how we could try to figure out if it's if what generates seems to be a cloud or not. But we plan to eventually train 3D models, 3D clouds to use our CNN with 3D clouds or something, another new kind of deep learning architecture for it. But right now, it was the simplest way to figure out what could look like a cloud or not.
Okay, great. Thank you again for your presentation and for the answers. And let's move on to the final paper. Okay, no problem. So let's move on to the last paper of the session. The paper is Assessing the Robustness of DeepQ Network Agents to Change on-Game Object Textures. It will be presented by Paulo Serafim from Instituto Atlântico.
Hello, everyone. Good morning. Thanks, Luis, for the introduction. So, okay. Can I start? Okay.
Go ahead.
Okay, thank you. This was a collaborative work with Instituto Atlântico and the CRAB Research Group at the Universidade Federal do Ceará. And at first, I would like to ask you to take a look on this image. And if I ask you what about is this image, probably everyone would tell me that is a tree. And that's right, because you can clearly see that is a tree, but if you observe carefully, it doesn't have leaves. It almost has no green colors. So if you pass this image to a vision-based classifier, it may say that it's not a tree because it's hard to to understand those kind of details. And this type of computer vision based algorithms models were used, for example, to play Atari games from DeepMind, which formed the basis of deep reinforcement learning, which was used, for example, in AlphaGo, which is very famous, and more recently in AlphaStar, which is the AI to play StarCraft 2 better than any human in the world. So in the last year's SBGames, we presented a work investigating if the deep reinforcement learning agents were able to generalize their performance for environments that were previously unseen. So they trained on different environments and played in another scene. For example, we have the basic Visdom scenario, and we created 3 custom scenarios, changing the first one, the Kakujimo, the monster, the other one changing the texture for flat textures with only colors, and then creating an animated version. Of course, we expected that if we train in one scenario and evaluate in the same scenario, the agent will have a good performance. But the other results we didn't know at the time. And what we observed is that, except for one case, the other one, the agent has a poor performance. So actually, what we saw is that the agents, at the moment, they were not able to generalize their performance when evaluating in scenarios that they were not trained on. Okay, but if you look carefully here, when we just changed the Kakujimo monster, we don't change the monster, the agent have a poor performance, but was a positive score, different than the other cases, except the one that achieved also a good behavior. And this was a motivation for us to evaluate what happened if we just change one single texture instead of changing the full environment. Okay, that was motivated those 4 questions. And if the agent is able to maintain its performance when changing only one single game object, and how the amount of pixel degradation are related to the performance. Okay, so this basically is this motivation of this work. We used the same methodology. This is the neural network. It is shallow compared with other ones that we see in the literature. And we used the same processing that take the screen, grayscale, resize, pass to the CNN, and then we extract the action values. But we actually used the exact same agents. We take the trained agents. They are freely available on GitHub. You can you can take a look on that if you want. So they were training those 4 scenarios, and we created 2 different experiments. The first one was we separated the individual textures of all the game objects. There are 4 game objects: the monster, the ceiling, the walls, and the floor. And we separated the textures that we created that were used in the previous work, and created scenarios based on the combinations of them. So we can freely use the flat monster with an animated walls and the original ceiling and things like that. So we created all of the possible combinations we can with those game objects and evaluated in this first experiment. And in the second one, we created interpolations between the scenarios. Okay, so for example, this first one, and at the leftmost side, we have only the original scenario, that is 0% of the animated scenario. And on the rightmost side, we have the 100% animated. So there is no contribution of the original basic scenario. Okay, and between we have 25% of pixels from the animated and 75% pixels from the basic scenario and things like that. Looking at the results, what we saw from the basic NCACO, this is something that was already evaluated in our previous work, and it follows the same results. But when we try different combinations, we start to get more interesting results. For example, when the agent was trained in the basic and flat, it was the single case that the previous work, the agent was optimal, so it continued to be optimal in all other circumstances. And when the agent was trained in the flat scenario, that was the first moment when we realized that there is an influence. Because as we can see, sometimes the agent has a poor performance. It basically don't do anything. And other times he is optimal. So the difference is when the monster is flat, as you can saw in bold, when the monster is flat, the agent has an optimal performance. So this is something very interesting for us. When we evaluated the basic and animation pair, what we have is that the agent has a poor performance basically always. A good performance is around 70. Okay, so but when only the wall was animated, it has an okay performance. And when we invert the case, when I was training the animated scenario, it has a good performance when the floor is animated. So there is some type of relationship here. Okay, in the second experiment, evaluating the blending, the interpolations, what we saw between the basic and Kakudimon versions is that as closer as the agent is to the original trained version, better would be its result. But when you go, for example, to the flat has something that we have to 50% because of the transparency things about the Visnu itself. And the basic the agent trained on the basic scenario, it performs optimal in all cases. But when I was training the flat scenario, it only starts to be good when actually the monster has the blue border. Okay. In the in the basic and animated scenarios, what we see is that after the 50%, there is a break. So the agent is better before the 50% if it was trained on the basic, and after it was trained on the animated. And what we can see from this is that answering our questions is the agent able to maintain its performance when we change the texture of a single game object? First, it depends on the training scenario, if it was trained on the basic scenario or the other pair. And in most cases, no, it can't. But for the second question, is there any kind of correlation between the agents and the game objects? We observed that there is some time of correlation, but it is not global. In one case, it was the floor. In other case, it was the monster. So there is not a single game object that is responsible for a optimal performance, for example. And is the amount of performance degradation related to the numbers of pixel changes? So using the interpolation, the blending scenarios, we observed that the degradation is related to the interpolation. So as closer as the agent is to the trained version, better would be its performance. Okay, and also this is the kind of pattern that we observed, but there is no, for example, linear correlation or things like that. It's just, it seems to be that way generally, but it's not a specific case of correlation. And this result suggests that it may be possible to avoid performance degradation if we focus more on the game object itself and not on the pixels of the screen. And for example, in the first experiment, we saw that in the flat case, if the monster has a blue border, the agent has an optimal performance. So if he knew what is a monster, probably it will have a optimal performance in all of the cases. And therefore, we should move trying to train the agents to learn things like enemy background and things like that. And as feature works, using those conclusions, we observe two different branches here. The first one is using more robust architectures. We could use, for example, autoencoders and semantic segmentation, or even things like recurrent neural networks that will be more complex, but can help us to understand how the agent could learn the concept of game object. And also the second branch would be take those results, the outputs of the agent, together with the input images, and try to interpret what the agent is seeing. So there's a recent research going on neural network interpretability and explainable AI using deep reinforcement learning. So there's another path that we can follow. And I would like to thank you, everyone, for your attention. And please feel free to ask any questions.
Okay, thank you, Paulo, for a nice presentation. let's check if we have some questions on YouTube or on the Discord channel. No questions so far. Let me just clarify a point. The score that you showed is basically the agent playing the game and the final score that it has on that scenario, basically.
Yes. The agent plays the game, and if it kills the monster, it receives a positive score of 100. So when it kills the monster fast, it obtains a score around 70, for example, without shooting. And every time he shoots wrong, he also loses some score. So if keep standing or just shooting and doesn't hit the monster, he would have a very negative score. So if he shoots the monster, but after trying to shoot in a lot of times, he would get a positive score, but a low positive score.
Okay, and how do you implement this agent algorithm? It's trained, it's also on a neural network, or it's a finite state machine? What's the type of algorithm that you use?
It's a neural network.
Okay.
We are using a convolutional neural network using GPQ networks as a reinforcement learning,
So
deep reinforcement learning
okay.
algorithm. Yes. So we are using but we did not train the agent at this point. We used the already trained agents from our work in the last years. So we take the already trained agents, since are the same environment, it can be used also.
Okay, so you use the already trained agent and check if the changes on the scenery will impact the performance, basically, right?
Exactly.
Okay. There was one question from Zé Ricardo. How do you calculate the negative score?
Okay, so this comes from the environment itself. So Visdum has this basic scenario ready. We use it, and we created the other 3 custom scenarios. Okay, but from the basic version, the Visdum, what it does is for every tick, the agent loses 1 point, so it receives a -1 score. So if you just keep standing and doesn't do anything, he will lose 1 score each tick, and there are around actually about the minimum value is around -250. So if the agent is just alive, he was already losing score. He just gained a point when he kills the monster. It's basically that.
Okay. We have time for one more question. Let's check here. A final question: did you try in other scenarios in different layouts, or all the tests were just changing the texture of that scenario?
At this moment, we just changed the textures. The difference is that instead of changing all the scenario, we changed specific game objects and created all the possible combinations, and also the interpolations that we would like to evaluate if there is any kind of correlation between the proportion of pixels from that one. But since this is the most basic case, and the agent is not able to generalize in the most basic case, we did not start yet with more complex. We just we are expecting to solve this problem for the basic case at first, and then move to more complex scenarios.
Okay, Paulo, thank you again for a good presentation and a nice work. This will end our session, our first session of the computing track of SBGames 2021, the session on procedural modeling. Before ending our broadcast, Professor Esteban Clua would like to make some welcome message and invite you for the next activities of the SBGames 2001. Esteban?
Hello, everybody. Thank you, Professor Luis. I am Professor Esteban, and together with Professor Bruno Feijó, we are the chairs of the computing track. We want to welcome everybody to the conference, to our track. We are very glad that there was many attendants at YouTube, Discord. So we invite you for the next activities. There's a lot of activities. Today we will have the open ceremony that will be at 1:30 p.m. And just after the open ceremony, we will have our first keynote with Professor Geber Ramalho, and he will talk, I will tell in Portuguese because the title of his talk is in Portuguese, Desenvolvimento e Operação de Jogos baseado em dados, recompensas e armadilhas. And the talk will be at 2:30 p.m., don't lose. And then we still have another activity from the computing track today, which is the short papers sessions. We will have 10 short papers that will be presented in a very fast forward, basically, process. It will be at 5 p.m., from 5 to 6 p.m. And after this, at 6 p.m., we will open a Discord coffee in order to discuss with the authors, and ask questions and have more informal interaction with everybody. Okay, thank you very much, everybody. I hope you have a great SBGames. In the name of the computing track, we also would like to thank for your participation here. Thank you.
Okay. Well, thank you, Esteban, and thank you, everyone, for watching, and hope to see you in the next activities. Bye-bye.